In this lecture, I will introduce you to generalized linear models, and in the next couple of lectures, we will actually learn to implement them in R. And so far, you've been dealing with models and regression models where we assume the error distribution or the error structure to be normally distributed, and if not, we try to make it normal. But there are some situations in which we have to accept that we are going to have a non-normal error structure to begin with, and that is when GLMs come into play. So we use GLMs in situations when the residuals are neither normally distributed and nor can we make them normal, and in fact it is not even advisable to attempt to make them normal, because the kind of issues we are trying to address with GLMs and the kind of data we are trying to analyze, they do not lend themselves to conventional modeling, linear regression modeling. GLM is used in situations when we have data such as biological data and the residuals are typically not normal. So that can include cases of proportions when we are trying to examine things like infection rates and survival rates. In this case, we should be examining these kind of data using GLMs. For count data, say insects on a leaf, trees in a plot, again, or butterflies in a forest, all of these are regarded as count data, and it is a whole integer number. You can have, say, 100 butterflies in one forest and 25 butterflies in another forest, and these are typically count data, and we should model them using GLMs. And then we have binary responses, dead, alive, present, absence, and these data also lend themselves to GLMs. So this is a typical linear regression equation that we are familiar with, and what do GLMs tell us and where do they fit in? These are flexible generalization of ordinary linear regression, and essentially we can use these to explain non-normal response data using explanatory variables, the way we put in a conventional linear regression. And in this case, we try to understand what external influences are represented using independent variables, drive the change in response variable. And the implementation of GLMs requires the residuals to have an alternative distribution, and we can analyze the relationship between response and predictors with regression using GLMs. GLMs, they generalize linear regression by allowing the linear model, which is, and you saw the linear model comprising of the predictor variables and the coefficients, to be related to the response variable via a link function, and we account for non-normal error structures. An error structure of the variable y can hail from exponential family, and this can be considered within the GLM framework. So the error structure can be normal, Poisson, binomial, gamma. Link function, or G, is the transformation of y used to linearize its values, and then the linear predictors like so. So essentially this linear link function will linearize the value of y, and then the linear predictors of variables x, they will be regressed against a transformed response like so. So this looks like a conventional linear regression model, but the only difference is that here we have a transformed response variable, and the common link functions are Gaussian. And when we have Gaussian error structures, we just carry out the ordinary linear regression. Poisson, binomial, this is the link function that we used for carrying out the bespoke transformation of our response variable, and need be for back transformations, etc. And in case this feels a bit confusing to you, for all practical purposes, two of the most common GLM models are logistic regression. This is used in cases when the response variable is binary and the error structure is assumed to be binomial, and Poisson regression is used for count data and the error structure is assumed to be Poisson. In the subsequent lectures, I will just show how you can implement these in R and go over the interpretation of their results.